Hello. Now, in this video, we are going to discuss about the mechanics of a system of particles after having considered the case of a single particle and the conservation theorem associated with it. Now, as for a multi-particle system, we can consider when we have a system of two or more particles, we can consider a system uh, where a force that will act on a certain particle can be given in this form, that is, the force on any ith particle considered is equal to the force on it due to an external agent, that is F external acting on I, which is the external force in that case. And then we have the case of internal forces where all the particles are applying the forces on one another, and Fij is the force on the ith particle due to the jth particle, j extending from 1 up to n for n number of particles, excluding the particle itself. Obviously, it cannot apply a force on itself. So from Newton's law, what we know that Fi is also going to be equal to the rate of change of momentum of that particle. So that is going to be equal to its mass and the rate of change of velocity. And that will be equal to the mass multiplied to the second order derivative of its position with respect to time. Now, if we are to consider the entire system, so the net force that may be acting on the entire system will be taken in this form, that is the second order derivative of the ith particle miri taken over the entire range of particles, that is from 1 to n. And then on the right hand side we'll have the case of external forces, the addition of all the external forces or the external forces acting on each of those particles added together, and then we'll sum it over I and j, that is the case of the internal forces where I obviously is not equal to j. So we have Fij, that is the force on the ith particle due to the jth particle, all of them summed over from the range 1 to n. Now, as we know about the case of the internal forces, we have the Newton's third law. From Newton's third law, we have the case of action and reaction forces where Fij plus Fji is always going to be 0 because they're equal and opposite. So in that case, the second summation will vanish. And as a result of that, we'll simply have the case where we have the second order derivative with respect to time of the sum of all the miri, that is the moment of mass you can say in that case. We'll get to that later, but that is equal to the external force, that is the net external or the total external force that is acting. Now, having considered about the system of particles, we must also consider the term called the center of mass. Now, the center of mass of a system of particles is going to be given in this form, that is the position of the center of mass, usually denoted by r vector, is equal to, or we can denote it as rcm, but nevertheless over here I have denoted as r. So that is equal to the summation of the product of miri and taken over all the total mass of the system, which includes the sum of all the individual masses forming the system. Let's take that as capital M, and above that we have the summation of miri vectorially. This gives the position of the center of mass of a system, the center of mass being the case where the entire mass of the system can be considered to have been concentrated. That is, if we are talking about the motion of an object, which comprises of the system of particles, then that motion of those system of particles forming the object will be considered finite only when there is a change in the position of the center of mass. If the position of the center of mass remains as such, then we will consider, even if the particles move, we will consider that the entire system as a whole is at rest. So the force, the external force that acts on the system, that will be equal to the mass times of the second order derivative of the position of the change in position with respect to the time, that is the second order derivative of the position of the center of mass, which will eventually give us the acceleration of the center of mass. So that is how we get to know, or that is how we get to uh, know about the system as a whole, about its motion, about its position, by knowing the position of the center of mass. We need not be concerned about the individual particles. As a whole, the system is always concentrated at the center of mass. And so the linear momentum of the system will be given by the variation of the multiplication of the mass of the entire system with the rate of change of the position of the center of mass, that is dr over dt, and that gives us m times the velocity of the center of mass. And the rate of change of momentum, that is p dot in this case, is obviously going to be equal to that is equal to the force applied, and the force, as we know, is the external force in this case, and that is equal to the rate of change of the momentum of the system as a whole, and that is equal to m times of the second derivative of the center of mass with respect to position of the center of mass with respect to time. And if the external force, that is absent, then we'll have the momentum to be conserved, that is p is equal to constant for the given system. So that tells us about the law of conservation of the linear momentum for a system of particles. Now, talking about the center of mass, we also consider the center of mass frame of reference, usually called as C frame of reference. And what is that? Well, in this frame of reference, the center of mass remains at rest. That means the velocity of the center of mass that we had obtained, that is the rate of change of position of center of mass with respect to time, well, that is kept constant, or that is set to 0. That means the position of the center of mass is constant. And so in this case, what we get is that for the momentum that we had discussed, we get m times of vcm, that will be equal to 0. And that is why the center of mass frame of reference is also called as the zero momentum frame of reference, or the zero momentum frame simply. This frame is very important in many kind of experiments that are performed in the laboratory, so as to simplify and analyze the entire problem as a whole. And usually, as you might have seen, that we had discussed about the scattering cross section, the problems involving the scattering cross section, and many more such collision related or explosion related experiments are based on the center of mass frame, which makes it really easy to calculate. Uh, it's better to just have an idea. As of now, we'll be dealing with the numericals associated with the center of mass frame of reference in the upcoming videos as well. As far as the angular momentum of the system of particles is concerned, if we have supposedly J1, J2, they are the angular momenta of the various particles of the system constituting the system, then the total angular momentum is equal to the sum of the individual angular momenta or momentum individually. For n number of particles, it extends up to Jn, which we can also write as the position cross product with the corresponding momentum of the particle, that is R2 cross P2, and so on right up to Rn cross product with Pn, momentum of the nth particle. Now, in general, this can be written as the summation from I going from 1 over to n Ri cross Pi. Now, as for the case of rate of change of angular momentum is concerned, dj over dt, we'll have the derivative. Now, the derivative will obviously be a product derivative, that is the derivative of the first term cross product with the second term and the derivative of the second term, and we'll keep the cross product first. But while considering the derivative of Ri with respect to time, that will yield a v, and Pi also consists of a v term, that is m times of Vi. So Vi cross Vi, that is going to be 0. So all we are going to have over here is simply the summation of Ri cross Pi dot, because Ri dot is going to vanish as I just said, and Ri dot cross Pi dot is going to cross Pi is going to be 0, and so we'll have the summation of Ri. Pi dot is the force, and that is what we get from the rate of change of angular momentum. As for Ri cross Fi, we can put the uh, expression for the force on the ith particle that we had discussed right at the very beginning. So we have Ri cross Fi comprising of the external force, then we have the summation over the I and J terms for all the internal forces, so Ri cross Fij. Now, the last term has a double sum, that is I and J going from 1 to n, and hence it is a sum of pairs of form that is given by Ri cross Fij plus Rj cross Fji, and that will be giving us Ri minus Rj, that is the difference in the position vectors of the ith and the jth particle, cross product with Fij, and that will be equal to Rij, the difference that is, and cross Fij. Rij is obviously this term that we just denoted. Now, because Fji is equal and opposite to Fij, so this last term that we are going to have, that will go to 0, taking the cross product, that will go to 0, and therefore what we'll get is that yes, that's going to be equal to 0. And why is that going to be equal to 0? Because the forces, suppose we have the ith and the jth particle, let me just give you an idea. So this line is where the Rij is going to be, because that is going to be Ri minus Rj. So this will have some position vector Rj, and this will be Ri, and Ri minus Rj is going to be along that direction, and the force that is acting from J on I, that is also going to be acting along that direction. So the force and the that difference lying along the same line, their cross product is going to be zero. So this term obviously is going to vanish. So we are going to set that to zero. Now what we are left with is that this is simply d by dt over dt of j, and that is equal to the summation of Ri cross Fi, that is the external force that is acting on the particle simply, and that is equal to nothing but the torque that is acting externally. And this torque will be, if that external torque is absent, in the absence of external torque, that is tau e is equal to 0, we'll have J to be equal to constant, that is the sum of all the angular momentum of the individual particles, that is going to be equal to a constant value. So that tells us about the conservation of the total angular momentum. Now, as we have studied about the linear and the angular momentum of the system of particles, most cases we found that the internal forces are cancelling out and they are going to zero. Well, that is the case when they are acting along the same line, but it's not the case every time for a system of particles concerned. We may have the case where two particles are acting exactly equal and opposite but not along the same line, and as a result of that, those internal forces are not going to cancel out each other. The action and reaction forces are not cancelling each other. We'll see a few examples later on as we proceed into the topic, into the higher uh, versions of what we are discussing, or into the deeper versions of what we are discussing. So it may be the case that the internal forces won't cancel out each other, and that is when we'll face some problem, and how we'll be dealing with them with the advanced form of the mechanics that we are going to use is what we have to study later on. Now, as far as the relation between the angular momentum and the angular momentum, the total angular momentum and the angular momentum of the center of mass is concerned, we have the relation as simply J is equal to the angular momentum about the center of mass plus the position of the center of mass cross product with the momentum of the center of mass. Which simply means that the total angular momentum of a system of particles about a point is the angular momentum of the system about the center of mass plus the angular momentum about the reference point of the system mass concentrated at the center of mass. So if we are considering a single particle out of that, so and we consider its position from the center of mass, then we'll have the total angular momentum to be represented in terms of the sum of the angular momentum about the center of mass and the angular momentum about that reference point that we are considering for the center of mass. We can consider another reference point apart from that center of mass, and it's going to have a certain position with respect to the center of mass, and that is how we relate them. Now, in order to explain that, we can just consider this figure where we have the center of mass over here, and it has a position R, capital R that is, and we have a point P where we have a particle of mass mi out of all the masses. We have the ith mass or the ith particle with the mass mi over there, and that has a position ri with respect to the origin, that is the point of reference, and ric over here is the position of the ith particle with respect to the center of mass. So what we are getting over here is that Ri is simply equal to R plus RIC, and if we take the first order differentiation with respect to time, we'll obviously get VI vector to be equal to VCM, that is the velocity of the center of mass, plus VIC, that's the change in position of the ith particle with respect to the center of mass, with respect to time, of course. And so the total angular momentum can be given as the sum of mi, that is all the ith particle, the mass of the ith particle, and as for this we'll be putting ri. So ri, as we know, is r plus ric, and then again we'll be doing the cross product with ri cross vi, and vi simply is vcm, that is the velocity of the center of mass, plus vic. Now if we do the cross product, we have the summation of mi. As for the cross product of all the terms, we'll have first of all r cross vcm, followed by, we can keep the mi summation outside, and we'll have the second term will carry r cross vic, and the third term being ric cross v, all in proper order, vcm, and the fourth term finally is ric cross vic. Now considering the first term, we have, well, r can be kept out of summation over here, so r cross sum over mi, and vcm as well is outside the summation, plus r again stays out, cross mi summed over vic, also included in that sum, and then we have the summation of mi ric cross vcm stays out of the summation, and then plus finally we have the term ric cross vic and mi. Now with all of that, we can have finally ric, as we know, is ri minus r. So this over here we have ric, over here we have ric is simply equal to ri minus, this is what we have written, ri minus r, which means mi ric, that is this term and this term, that is going to be equal to the sum over mi ri minus the sum over mi r, which is the position of the center of mass, and this is nothing but equal to mi ri summed minus the total mass times of the position, because summation of m is going to give me the total mass. And as for mr, we have that to be equal to simply all the terms, that is mi ri summed over, because that's what the property of center of mass is. So that means that eventually leads us to the fact that this is going to be equal to 0, which also tells us that the last two terms are going to be 0. So what we have for J is that J is equal to R, and as for this one, summation of Mi is going to be M, and times of VCM. That's the first term, and the second one is going to be, now there's one more term that we must consider, that is MIVIC is also going to vanish for this term, that is MICRIC going to 0. We'll also have this term summed over to go to 0. And as a result of that, well, not this term, because Mi is, well, that can be multiplied over here. This term will cancel out to go to 0, so will this term. So what we are left with is simply the summation of RIC cross MIVIC. Now why the Mi was multiplied over there? Because that is going to give us the momentum of the ith particle, and the distance, the position of the ith particle from the center of mass. This will tell us about the JCM term that we had considered, that is the momentum of the system, the angular momentum of the system about the center of mass. And as far as this is concerned, this will simply give us R cross P term, that is the center of mass, the angular momentum of the center of mass itself. So the total angular momentum is going to be equal to the sum of the angular momentum of the center of mass plus the angular momentum about the center of mass. And as far as the energy of the system is concerned, the total energy of the system is always going to be the same. So as far as the conservation of energy, we'll follow the same procedure as in case of the single particle, only thing in this case being the case of having learned about the cases of angular momentum and the linear momentum, we can generalize the energy terms in similar manner. And for the work done by the forces on the various particles of the system from an initial configuration, let us say initial configuration is 1 to a final configuration 2, we'll have the change in the kinetic energy from the work energy theorem working on it. We'll have T2 minus T1 to be equal to the amount of work done, and that will also be equal to V1 minus V2, taken in because we are always considering the negative way of it. So del V is V1 minus V2, and that is also equal to this. And so we put them together, so we have V1 minus V2 to be equal to T2 minus T1, or we have T1 plus V1 to be equal to T2 plus V2, which tells us that the total energy of the system is going to be conserved. The next video in this series of the introductory ideas will be dedicated to some of the numerical examples related to this topic. So stay tuned for that. That's all from this video. Till next time, thank you for watching.